All right, this is Professor Lewis, and we're talking about Module C, Week 1 here. And basically, we need to talk about beams and beam diagrams, and this is going to kind of relate to what we learned in the theory course, or some of you are doing concurrently. When we have a beam, and I'm going to kind of put it up here, and we take that beam and we bend it. So if I take a piece of foam and bend this foam, what we're going to see, we have this illustration, we're creating a moment in this direction and a countering moment on this side. We're going to bend that beam, and the top portion is going to have compression, and the bottom side is going to have tensile forces or tension on it. So if I'm looking at this picture here, I'm seeing that the compression is going to be here. And if you notice, the compression is variable as we go through here, just like the tension looking at this is going to be variable. And so when I take a cross-sectional cut of that beam, somewhere within that beam, I'm going to see that we have a neutral axis running through here. Let's look up here. See, we're showing our neutral axis right there. At that neutral axis, there's basically zero stress happening. That's the transition line from the compressive forces to our tensile forces. Now, the forces are going to grow larger as you get closer to the surface away from that neutral axis. And you guys kind of remember that from theory. Here's a beam we have simply supported. We have a pinned connection, so this is going to have a X and a Y component here. This is a roller connection, just having a single Y component. You guys remember the standard symbols for simply supported type beams. And we're just going to put a point load on that beam, and we're going to take a cross-sectional cut across it. Now, it could look like an I-beam like this one down here, or it could be a square member or a round member, but we're going to take a cross cut. And let's assume that blue beam is an I-beam here, for example. What we're going to see are the forces being higher. Now, we have different kinds of forces in here. These are going to be our normal forces. They're going to be the internal forces within the member. And this is going to be where we're going to see some of that stress. We're going to see the highest stress being out here. That's why in a I-beam like this, they're going to put more material up here than down in the web of the beam down here, because there's not as much stress there. So we're going to counter the stress with more material and place that material smartly up there where it belongs. And so we can see that we're going to have compressive and tensile forces within that beam. Now, within that, we're going to have our internal shear forces and bending moments. You guys did beam diagrams where you did shear and bending moment diagrams. We're going to do that here in just a minute and do a quick refresher. But basically, we have shear forces that are going to act on that member, and we're also going to have a resultant bending moment about that member. Now, when you're doing your lab, I want you guys to do your math and calculate your moments by using engineering paper, and you need to do it like an engineer would do. This is a demo problem, so this is an example of what we expect to be turned in. And you have the given. You're going to write down what is the beam going to look like here. I've got a 500-pound load. I've got simply supported, pinned over on the left side, and a roller on B. We're going to find and plot our shear and moment, because in this lab you're going to need to be having the moment about that beam at different places within that beam to calculate the stress on the surface of that beam. Now, we have strain gauges on there that we're going to be able to use as well, and we're going to be able to compare the two and make sure everything looks good. Now, with anything that we do, we're always going to start a problem with a free body diagram. So you need to draw a complete free body diagram. We know we have two reactional potentials with a pinned connection, one in the Y and the one in the X. Since we don't have any X forces, we know those are going to be equal to 0, but we still show it in our free body diagram. We have on the roller side just one force going up, that's at By. We have our 500 pounds, and this is our free body diagram. Once we have that, it makes it real easy for us to apply the equilibrium equations that we have, where the sum of the forces, sum of the moments, all those things are going to equal to 0, because we're in static status here. And looking at this beam, if I was trying to solve the Y directions, I've got two unknowns. That's not good. But if I solve the moments about A here, and that's what I've done here, I have one known and one unknown, I could solve for By, and that's what we did here. Now, I put a little hint here because you guys need to show your math with your units and everything. If I sum the forces or sum the moments about A, it's going to be equal to 0. And so when I do this, I need to say, okay, I have at 4 feet 500 pounds, and that is going clockwise about A. And I just put this as a hint. Remember, that is a negative moment. So we need to put a negative on that. Now, the BY is at 10 feet, and it's going up in a counterclockwise manner right here. So that is a positive moment. When we solve this, we're going to find out that this is going to tell us if BY is up or down, and our math says yes, it was correct. We always guess positive in our guesses for things like AX, BY on these. Just kind of a refresher from strengths class. Now that I know BY, I can solve the sum the forces about Y, come in here and plug all those things in and solve for that. I now know the reactional forces of this beam. Now, if you notice, I'm using a ruler and using the grids on my engineering paper. And if it helps, use color. I like color because it helps out for me to explain this to you. The first thing we're going to do is we're going from a load to a shear diagram now. So this is our shear force diagram, and it's in pounds. Okay, pounds force. It's a shear force unit on this one. And I'm going to draw my zero line all the way across the beam here. And what I'm going to do is I'm going to kind of come down here. I'm going to look at the minute I'm at point A right here. I have a force. That is AY. AY was 300 positive. I'm going to come up 300. And if I look at my beam, nothing changes until I get to that 500-pound load. Okay, there's my 500-pound load going down in a negative direction. So then I just drop down 500 pounds. Then what do I need to do? Well, nothing really happens to that beam until I get to this other reactional point, and then I have a 200 positive load, a shear force on there, I should say. And then that brings us back to zero. It always should go back to zero here. So now I can color this in, and I can see I have some positive shear force and some negative shear force over here. And that's going to be my shear force diagram. Now, this is basically like calculus. We go to one degree of a curve to the next. We have a square profile, so the next profiles are going to be triangles that we have on this diagram. And so it's the next order of curves that we see. And what we're going to see here is basically the bending moment, and that's going to be in foot-pounds. So we're going to be able to take these pounds and the distance, so that's basically the area of this section right here. So that's what I did right here. I took the area and said 4 feet, so from here to here was 4 feet, times that 300 shear force, and I got 1,200 foot-pounds of shear bending moment being generated. Okay, went ahead and figured out this area as well because I have a negative area here. Now let's go look at this thing. I'm going to look at this diagram. There are no moments about A or B. If I'm doing a counter-levered beam, I will have a moment. So you need to apply that moment at the counter-levered to that diagram. So it may have you automatically start up and then come down or go up depending on what your beam and the loading situation is. So don't forget that you may have to include the bending moments on a counter-levered beam into this. If you have questions about that, ask me or one of the TAs and we'll help you out. What we have here is, I'm going to put this where we can see both diagrams here. We're going to start off at zero. There's zero bending moment there. We're going to take this area, which was 1,200, and we're going to come to where it takes in effect right here and come down and plot this point, and that is going to be 1,200 foot-pounds right there. And since this was positive, this was going up positive. Now this is a negative 1,200 foot-pounds, and that's going from here to here, that's 6 feet, so it's going from here to here in a negative direction, so that says it's coming back to zero there. And this is our bending moment for that beam, if you wanted to. So now we know how to calculate our bending moment anywhere along that beam by figuring out the placement of X here. So if I wanted to figure out halfway, if this is 4 feet, if I wanted 2 feet, I could have came in here and said, well, 2 feet times 300, and I could get that point right there. And now I can get that because sometimes in your lab, the strain gauges are not placed always in the center. You have some in other places, and you're going to have to find that out. And that's going to help you out because all you need to do is go back to this diagram, figure out your displacement, go back to this portion, change that number right there, and you can say, okay, I know that basically from right here, if I was to draw a line all the way straight down, that basically I'm looking for this point. I'm at 2 feet. And the area is only 2 feet at 300, that would be 600, so I'm at 600. And that would make sense on our diagram here. Now then, we have a variable called I, and I we know as a sectional property of materials. It is the moment of inertia, and this is going to tell us the properties of that structural shape, basically. And so the units on this is always to the fourth power. So if it's in inches, it's probably inches to the fourth. If it's in metric, it's probably millimeters to the fourth. Typically, that's what we express it as. So you want to make sure you understand that the I values are going to be to the fourth power. Uh, Equation all engineers should know, and you need to remember this one, is for a simple square or rectangle, the area is base times height. That's easy. But the I value, now we have Ix and Iy. If I'm taking it about this axis, which that's what we're going to be doing in class, is taking it across the x-axis here, we're going to be using the B and the H are really specific in terms of the strength and the orientation of that beam. The Ix value is going to be a lot larger here than the Iy value, because if we look at the equation here, B, which is going to be smaller than H, that's okay, we can put that there, but look at what happens to H here. This H is cubed. Now, how do we get to the fourth power? We got cubed here and then inches, so you got inches times inches to the cube, that's inches to the fourth. This height, if we could have a bigger number being cubed, then we're going to have a lot larger I. It's going to be a lot more resistant to bending moments. Okay, and then we like that. So we would want to orientate the beam in the correct direction, because if we did the I about the Iy here and we were bending the other direction, if you look at this, the B is cubed and that's the smaller number. It's not as rigid of a beam. Now we have different shapes up here. Circles, you have the area for a circle. You should know the formulas for area circle. What is the area of a circle? Some of you probably know it as pi d squared over 4, or some of you just know it as pi r squared. Okay. We have the I value here, which is going to be, it's going to be the same about the x and the y on this, so that's why they say they're equal. It's going to be pi d to the fourth, that's the diameter, over 64th. So you need to remember that equation as well. Now when we get to circles that have a hollow portion, so like a tube or a pipe, and there's different definitions and meanings for those, but what we need to do is account for the material out here and not the material in the open part of that tube or pipe, that cross section. And so what's happening is basically they're just subtracting the I value for the whole circle, and then they find the I value just for the inner portion, and they subtract them here. So it's basically this I value equation is the same, it's just they're subtracting these two, and that's what's happening there. Okay, so we're just subtracting that. So if we're looking at the square here, we have a square. What if we have a square tube, which here's a rectangle tube, and you guys are going to probably have some rectangle and some square tubes in your labs. Again, I'm going to find the I value for the whole thing, BH cubed over 12. I'm going to find the I value just for the inner portion that's hollow. I'm going to subtract this value from that value, and now I can get the I value, the resultant value for that hollow section that we have that's a rectangular prismatic shape. Now, in your strengths books, and you guys will do in class, we talk about deflection, and you guys are going to be measuring deflection in this lab. And we talked about in the other video how to measure that. We're going to probably have a simply supported beam here, put a load in there, and in your books it has equations in terms of finding the maximum deflection. So this is deflection maximum, and what we can do is come in here and put our load, our length of the beam, and our values for E. Now what is the value for E? That is the modulus of elasticity. That's how rigid the material is. That's that slope on the stress strain diagram saying that this is Hucknodian material. And for aluminum, we're typically, and you may want to check the lab sheets, but typically around 10 to 11 mega PSI if you're in the inch system. If you're in looking at steel, then it's probably upwards of around 29 to 30 mega PSI. Okay, so we know that steel is going to be more rigid than aluminum. Also, our I value is down here. So if we have a larger I, then this is going to have less deflection as well. So we can see that relationship by the equations there. And so in your book, it's going to have a lot of different beam diagrams and stuff. Here we have a nice counterlevered beam. Hey, you guys got a counterlevered beam in class, and here we show counterlevered by a wall with a bunch of lines here, and we have the equation for the max there as well. Now, this brings us to a concept in the lab that you guys are going to have to calculate the stress somewhere along that beam. okay? And I've put both beams up here, two different demo beams of a simply supported and a counterlevered beam. I've put the load here. That load could be anywhere through here. We did a similar problem up there and calculated the beam diagrams for that. You could easily do a beam diagram for a counterlevered beam as well. But in your lab, you guys are going to be worried about what about that stress along that beam. And so the stress on the surface in this equation right here in your lab sheet will work for both simply supported and counterlevered beams. And I'm not going to go to the derivation of this equation, but we're going to give this to you, and it's on your lab sheet. Basically, we can have plus or minus because that stress could be compressive. That would be a negative. Need to know that. If it's positive, then it's in tension. Okay, so you need to keep track. Is my moment positive or negative? Pay attention to the lab if you're measuring the stress at the bottom of the beam or the top of the beam. Is it bending which direction? Okay, if I was looking at this counterlevered beam, I would expect to see what? Tensile forces on the top and compressive down here, opposite of this. Okay, so my beam diagrams are going to look different for those two members. Now, when I look at this equation, you guys have the bending moment. That is the bending moment at whatever place I want to pick. So if I wanted it 2 feet out like we did before, I could say, okay, 2 feet from here. Or if I do it where the load is, that's 4 feet. That's going to be my maximum bending moment probably, as we saw in that beam diagram up here. If I scroll back up there and look at that, remember that's our maximum bending moment. So I could come in there, put my bending moment. Now that's going to, because I'm dealing with the displacement in X here on these beams, that is going to change, and that's going to represent that the stress on the surface is not going to be the same all the way across because we're using that moment diagram that we talked about, and it's taking into consideration the variability of the bending moment force that we're going to see on there, the bending moment. The height of the beam. So we need to know the height of the beam. That's the height of the cross section. We need to know the moment of inertia. So you're going to calculate those I values. You're going to put this in there and calculate that out. Now, I wanted to take 1 second here just to kind of show you something cool. This is a FEA. This is a finite element analysis of a beam. Now, I did this in metric units here, and we have a counterlevered where it's fixed on this end, and I put a load on the beam here. I know it shows it bent over because the beam's kind of in deflection mode on this simulation here. And the beam will kind of want to bend down. Now, if I was looking at the stresses in this beam, remember you're calculating stresses here, what do those stresses look like? Well, if I was looking at the moment diagram, I'm going to see that the biggest moment is probably going to be about this end down here, and I'm going to see the highest stresses down here. Now, let's talk about what's going on over here, because eventually you guys have the potential to take some FEA courses and more advanced courses past strengths and materials that will do this kind of stuff. And what we do is we simulate, we mesh, make like a screen network of nodes across that part, and we do lots of calculations. And we apply the material properties from node to node and the forces that are applied, and we can actually make a nice colored plot like this. And this is a plot that's going to show us what we call von Mises. Okay, that's kind of our combined stresses. We're showing that in Newton meters. So I'm in metric on here. If it was inch, it would be PSI on there. So we have pounds per square inch. So we have a nice colored plot over here, and we don't know if red is good or bad. It's bad in this case because I see this arrow right here, and that's showing my yield strength of the material for this material in the simulation. So I have to tell it the material and the material properties. And the load that I put on, the distance and all that, it's saying that for this beam, my stresses on the surface or anywhere in that beam, look at the center, it's blue. Out here's blue. There's not a lot of stress out here. Look at this. It's blue. There's not a lot of stress out here. Where do my stresses generate the highest on this counterlevered beam? Right here next to the connection to the wall. And I can see that it's red, and that is beyond what the material can handle. So I would be kind of concerned about this. I don't have any kind of safety factor applied to this, that I potentially could have failure of this beam right here potentially because of the high stresses. So we're doing that kind of fun stuff. I believe in strengths and material, we actually have you guys for the first this year doing a little bit of FEA, comparing some things on some frames and trusses that you guys build. So if you're looking for a fun course, maybe you pick up a little bit of this in there. I hope this helps out, and we'll see you in lab.